Let's talk about LangGraph and more specifically how to build stateful AI agents that can actually handle production workloads. LangGraph is a framework that sits on top of LangChain and is specifically designed for creating what we call stateful multi-actor applications with large language models. Now the key word here is stateful. Unlike simple chain-based approaches where you just execute a linear sequence of prompts one after another, LangGraph introduces the concepts of graphs. In these graphs, nodes represent continuous units and edges define how execution flows between these nodes. So why does this matter? Think of it this way. When you build a simple prompt chain, you have a step 1, then step 2, and then step 3, and then your LSI done. But real world AI applications rarely work that way. You need to have the ability to loop back when your first attempt does not succeed. You need to branch based on conditions in your data. You need to retry when something fails. And you need to maintain state across multiple interactions with the user. LangGraph gives you explicit control over all these patterns. The framework essentially treats your AI application as a state machine. Each node in your graph can read from and write to a shared state object, and conditional edges determine which node should execute next based on the current state. This is fundamentally different from traditional prompt chaining because it gives you explicit control over cycles. Your agents can iterate on a problem, reflect on their outputs, gather additional information, and refine their results before producing a final answer. From a practical standpoint, LangGraph supports both synchronous and asynchronous execution, which makes it suitable for real time applications where users are waiting for responses, as well as batch processing workloads where you need to orchestrate multiple LLM calls efficiently in the background. This architectural shift from linear chains to graphs is what enables you to build production grade agents that can make decisions, recovers from errors, and adapt their behavior based on the intermediate results. Now let's talk about state architecture, which is really the central nervous system of any LangGraph application. If you understand state well, everything else in LangGraph becomes much easier to grasp. The state in LangGraph acts as a shared memory that flows through every single node in your graph. You define the state using TypedDict in Python and you specify exactly what data in your graph needs to track throughout your execution. This could include the user's original input, conversation history with all the messages in exchange, intermediate results from various processing steps, flags that control routing decisions, and really anything else your application needs to remember as it moves through the graph. Now, here's where it gets interesting. Each field in your state can have what's called a reducer function associated with it. The reducer determines how updates from different nodes get merged together. By default, the reducer simply overrides the previous value with the new one. But you can also use operators like the add operator for list, which can accumulate messages or results across multiple nodes rather than just replacing them. This is particularly useful for things like conversation history, where you want each node to append its messages rather than simply replacing the entire history. This reducer pattern becomes crucial when you have multiple nodes executed in parallel and they both try to update the same state at the same time. Without proper reducers, you have race conditions and unpredictable behavior. With reducers, you have explicit conflict resolution strategies defined right there in your schema, so the behavior is deterministic and predictable. When you're designing your state schema, you want to think carefully about what information needs to process across the entire graph execution versus what's only needed temporarily within a single node. A well-designed state schema typically includes the input data that started the whole process and intermediate results that downstream nodes will need to access, a message history for conversation tracking, and flags or counters that counter your conditional routing decisions throughout execution. One important detail to understand is that state objects are immutable from the perspective of individual nodes. Nodes receive a copy of the state, they do their work, and then they return updates rather than modifying the state directly. This immutability is what ensures predictable behavior and enables powerful features like checkpointing, where you can save the state at any point, and time travel debugging, where you can replay the graph from any previous state. Let's talk about nodes, which are the fundamental building blocks of any LangGraph application. Understanding nodes well is essential because this is where all your actual logic lives. Nodes in LangGraph are simply Python functions. They take the current state as input and they return a dictionary containing the state updates they want to make. The key insight here is that you follow a partial update approach. You don't need to return the entire state object, just the fields you want to modify. LangGraph handles merging those updates back to the full state using reducers we have discussed earlier. Inside a node, you can do essentially anything. You can make LLM calls to generate text or make decisions. You can execute tools to interact with external systems. You can perform data transformations to prepare information for downstream processing. You can call external APIs to fetch or send data, or you can run the arbitrary Python code that your application needs. The key design principle is that each node should have a single, well defined responsibility. The separation of concerns makes your graph much easier to debug, test, and modify over time. In my experience building these systems, there are several common node patterns that emerge in production applications. You might have a planning node that analyzes the user's requests and decides what actions need to be taken. Then you have a tool execution node that actually runs those tools and captures the results. You might have a reflection node that evaluates whether the results are satisfactory or if another iteration is needed. And you might have a synthesis node that combines information from multiple sources into a current output for the user. Nodes can also access configuration and runtime information through a second optional parameter. This allows you to pass in things like model parameters that control how the LLM behaves, API keys for external services, or user specific settings that can customize the experience. This keeps your state schema focused on the actual data flowing through your application rather than being cluttered with configuration concerns. For production systems, proper error handling within nodes is absolutely critical. You should implement try catch blocks around any operation that might fail. You should add meaningful error messages to your state when things go wrong so downstream nodes and debugging tools can understand what happened. And you should think carefully about what state updates should happen when failures occur because this allows downstream nodes to respond appropriately rather than failing silently or crashing the entire graph. Now let's move to edges, which control how execution flows between nodes in your graph. Understanding edge types is what allows you to build sophisticated routing logic in your applications. LangGraph provides three types of edges that you need to understand. First, we have normal edges. These create a fixed connection from one node to another. After the source node completes, the target node always executes next, no questions asked. These are useful for sequential processing steps that always occur in the same order, like pre-processing followed by main processing. Second, we have conditional edges, and this is where things get really powerful. Conditional edges introduce branching by calling what's called a router function. This router function examines the current state and returns the name of the next node to execute. The router receives the same state object as regular nodes, but instead of returning state updates, it returns a string that identifies which node should run next. This allows you to build complex decision trees, error handling paths, and iterative loops all within the same graph structure. Third, we have entry edges. These define where your graph starts and which node executes first and when you invoke the graph. You can have multiple entry points and use conditional logic to select among them based on initial input. This is useful when you have different processing paths for different types of requests. There is also a special constant called end that represents graph termination. You can route to end from any conditional edge when your application has completed its work, either successfully with the final result or after determining that further processing is not possible or necessary given the current state. One piece of advice from building these systems in production I will give you is that keep your router logic simple. Base your routing decisions on clear state values rather than complex computations. If your routing logic requires significant processing, move that processing into a dedicated node that sets a routine flag in the state. Then your conditional edge just reads that flag. This pattern keeps your graph structure clean and makes the decision point explicit and easy to understand when you're debugging or explaining the system to teammates. Let's talk about cycles, which are really what distinguish LangGraph from linear change approaches and enables true agentic behavior. This is where LangGraph really shines compared to simple orchestration patterns. The ability to create cycles means your agents can iterate on problems, gather additional information when the first attempt is not sufficient, and refine their approaches based on intermediate results. This is fundamentally different from linear change where you get one shot at each step and then you're done. A typical agent loop consists of three main components. First, you have a reasoning node where the LLM analyzes the current situation and decides what action to take next. Second, you have a tool execution node that carries out the action and captures the results. And third, you have an evaluation node that examines the results and determines whether to continue looping or terminate by routing to the end constant. The cycle continues until the evaluation node decides it's time to stop, either because the task is complete or because some termination condition has been met. Now, here's something critical for production systems that you absolutely must understand. You must implement iteration limits. LLM based agents can get stuck in infinite loops when they encounter edge cases or confusing inputs. I've seen this in production where an agent just keeps trying the same thing over and over because the LLM does not realize it's not making progress. The way to handle this is to include a counter in your state that increments each time through the loop. Then your conditional edge checks this counter before allowing another iteration. If you hit the limit, you route to end constant with whatever results you have, and perhaps a message explaining that the maximum iterations were reached. The react pattern, which stands for reasoning and acting, maps naturally to LangGraph cycles. In React, the agent alternates between reasoning about what to do and then acting on that reasoning. This creates a two-node cycle connected by conditional edges, and it performs the foundation for most agent architectures you will see in production systems today. More sophisticated patterns can build on this foundation. You might add a reflection node that critiques the agent's progress and suggests course corrections. You might have a replanning node that adjusts the overall strategy based on accumulated evidence from previous iterations. Or you might have human checkpoints that pause execution for approval before continuing with high stakes actions. These all build naturally on the basic cycle pattern. Let's talk about how to integrate tools into your LangGraph agents because tools are what allows your agents to actually interact with the real world and accomplish useful tasks beyond just generating text. LangGraph provides seamless integration with LangChain tools. You can define tools with the tool decorator or by creating tool objects with a name, description, and a callable function. The name and description are particularly important because they help the LLM understand when and how to use each tool. A poorly described tool will be used incorrectly or not at all. The tool node class is your friend here. It handles the execution of tools that the LLM selects. When the LLM returns a message containing tool calls, the tool node automatically parses the information, invokes the appropriate functions with the provided arguments, and packages the results as tool message objects that get added to the conversation history. This creates a clean abstraction so you don't have to write all that boilerplate yourself. This creates a natural loop in your agent. The LLM can request tool executions, receive the results in conversation history, reason about those results, and then decide whether to make additional tool calls or generate a final response to the user. Multiple iterations of this loop allows the agent to accomplish complex multi-step tasks. One performance optimization to be aware of is parallel tool execution. When multiple tools are called simultaneously and their results don't depend on each other, LangGraph can execute them in parallel. This significantly improves performance compared to running tools sequentially, especially when tools involve network calls or other operations with high latency. When you're designing tools for agents, I cannot stress enough how important good descriptions are. You should be providing clear, detailed descriptions that help the LLM understand exactly when and how to use each tool. You should include the information about required parameters and what they mean. You should describe what kind of return values they expect as well. And definitely mention any limitations, error conditions that might occur. The quality of your tool descriptions directly impacts how well your agent performs. Also, test your tools extensively in isolation before integrating them into your graph. Debugging tool failures within a complex agent loop is significantly more challenging than debugging standalone tool functions with controlled inputs. Save yourself the headache and test thoroughly upfront with a variety of inputs, including edge cases, especially in production. Let's talk about human in the loop patterns, which become essential when you're building agents that handle high stake decisions when you cannot afford to have AI that makes mistakes autonomously. Human in the loop capabilities allow you to pause graph execution at designated points, present information to a human operator, and then resume execution based on the input or approval. LangGraph implements this through the interrupt underscore before and interrupt underscore after parameters when you add those nodes to the graph. These parameters specify in that execution should pause whether before or after that the particular node runs. When an interrupt occurs, the graph state gets persisted to your checkpointer and a special interrupt value returns to your application code. Your application can then display the current state to a human through whatever interface you have built, whether that's a web dashboard, a Slack message, an email, or any other channel. After collecting the input, you resume the graph using the command primitive to inject the human's response back into the state, and execution continues from where it's left off. This pattern is essential for applications where certain actions require human approval before they can proceed. Think about scenarios like sending emails on behalf of a user where a mistake could be embarrassing or damaging, or making purchases where real money is involved, or for example, modifying a database record where incorrect changes could correct important data, or really any action with significant real-world consequences that cannot be easily reversed. In all of these cases, you definitely want a human in the loop. You can implement different patterns depending on your needs here. Approval gates are where the agent proposes an action and simply waits for a human confirmation before proceeding. The human either approves or execution continues, or they reject and the execution stops or take an alternate path. Rejection handling is more sophisticated, where humans provide feedback explaining why they rejected the proposal, and the agent uses that feedback to generate a different proposal that addresses their concerns. The key architecture decision you need to make is identifying which nodes represent actions that warrant human oversight versus those that can execute autonomously. This often depends on the risk profile of your application, the reversibility of each action, and the potential consequences if something goes wrong. In my experience, it's better to start with more human checkpoints and relax them over time as you build confidence in your agent's behavior, rather than starting too permissive and dealing with the consequences of mistakes. Let's talk about persistence and memory, which are what allow your LangGraph applications to maintain state across sessions and survive restarts. Without persistence, your agents forget everything every time the process stops. Persistence enables your applications to survive process restarts without losing your progress and support long running conversations that can span multiple sessions over hours or days and maintain state across user interactions. The way this works is that through the checkpoint abstraction, which automatically saves graph state after each node execution, this creates a recoverable snapshot that includes all the state values plus metadata about which node just executed and what the next steps should be. LangGraph provides built-in checkpointers for common storage backends. You can use SQLite for local development, which is simple to set up and requires no additional infrastructure. For production deployments, PostgreSQL is a solid choice that gives you durability and the ability to query your checkpoints. And Redis is available for high performance caching scenarios where you need extremely fast read and write operations and can tolerate some data loss in edge cases. Each conversation execution thread is identified by thread underscore ID that you provide when invoking the graph. The checkpointer uses this identifier to store and retrieve the current state for each conversation. When you invoke a graph with an existing thread underscore ID, the checkpointer automatically loads the most recent state and resumes execution from where it left off. This makes implementing features like conversation continuity straightforward. This enables several powerful patterns in your applications. You can build conversational agents that remember previous interactions across sessions so users can pick up where they left off. You can build multi-step workflows and span multiple API calls even if there are hours or days between each steps. And you can build resilient systems that can recover gracefully from failures, including server restarts and crashes, without losing all the progress made before the interruption. Beyond simple checkpointing, you can also implement cross-thread memory. This means storing and retrieving information in a separate memory store that persists independently of individual conversation threads. This allows the agents to learn user preferences over time across all their conversations, accumulate knowledge from past interactions, and personalize their behavior based on historical patterns. This is how you build agents that get better the more that you interact with a particular user. Let's talk about subgraphs and hierarchical composition, which allows you to build complex applications from smaller reusable components. This is how you manage complexity as your agents grow more sophisticated. Subgraphs let you compose applications from smaller graph components, creating a hierarchical structure where one graph can contain another graph as a node. When you add a compiled graph as a node in parent graph, LangGraph can handle the state transformation between parent and child automatically based on the overlapping state fields. Fields with the same name flow naturally between the two levels. This enables some powerful architectural patterns that help you manage complexity. You can create a specialized sub-agents that can handle specific domains, like one agent that's expert at database queries and another one that's expert at document analysis. Each can be developed and tested independently. You can build reusable workflow components that can be shared across multiple applications in your organization, reducing duplication and ensuring consistency. And you can also build multi-agent systems where different agents have different capabilities, but they coordinate through a shared parent graph that orchestrates their interactions. The way it works is that the parent graph invokes the subgraph, which then executes its entire internal logic independently. When the subgraph completes, control returns to the parent with the updated state values, and that reflects what the state subgraph accomplished. State namespacing prevents conflicts when parent and child graphs happen to have fields with the same name but different meanings, so you don't have to worry about accidental collisions. Configuration can pass from parent to child, allowing you to customize the child's behavior at runtime based on context from the parent. And crucially, subgraphs can be tested in isolation before you integrate them. This ensures each component works correctly on its own with well-defined inputs and outputs before you add the complexity of integration. Good candidates for subgraphs include domain-specific reasoning chains that encapsulate expertise in particular area, standard approval workflows that you use across multiple applications, tool execution pipelines with their own retry logic and error handling, and really any pattern you find yourself re-implementing across multiple graphs. By extracting these into subgraphs, you centralize the maintenance and testing, which pays dividends as the system grows and evolves over time in production. Let's wrap up by talking about production deployment and optimization because building the graph is only half the battle. Getting it to run reliably at a scale is another half. Deploying LangGraph applications to production require attention to reliability, observability, performance, and operational concerns that go well beyond the core graph logic you have written. LangGraph platform provides the infrastructure for deploying your graphs as scalable services. It has built-in support for long-running executions that might take minutes or hours to complete, automatic retries when things fail due to transient errors, and horizontal scaling across multiple instances to handle production traffic as a user base grows. For observability, integration with LangSmith enables comprehensive tracing on every node execution, every LLM call, and every tool invocation. This gives you visibility into how your agents behave in production and helps you identify performance bottlenecks or logic errors that need attention. When something goes wrong, you can trace exactly what happened step by step. Error handling needs to happen at every level of your system. Tool functions should catch and report errors gracefully rather than throwing exceptions that crash your graph. Node should handle unexpected LLM outputs because models will surprise you with responses you didn't anticipate. And your graph structure should include fallback paths when your primary approaches fail, so your users will still get reasonable response when things go wrong. You should consider setting appropriate timeouts for LLM calls and external API requests. Without timeouts, there could be long executions will consume resources indefinitely and your system will eventually degrade. You should be monitoring key metrics including execution latency, token usage, which drives your costs, error rates, and iteration counts on your agent loops. These metrics help you understand your agent's behavior and cost, and they alert you when something is going wrong. For high traffic applications, consider implementing rate limiting to protect downstream services from being overwhelmed. You should add request queuing to handle traffic spikes gracefully when you get more requests than you process immediately. And you should also implement graceful degradation for scenarios where demand exceeds the capacity so your users get a reduced experience rather than a complete failure. You should also look at caching frequently accessed data and consider whether certain LLM calls can be replaced with faster rule-based logic for common cases. If you see the same question asked repeatedly, caching the response can dramatically reduce latency and cost. Finally, version your graphs and maintain the ability to roll back to previous versions. When you deploy updates to productions, things can go wrong in unexpected ways. Having a quick rollback path gives you confidence to iterate quickly while maintaining reliability to your users. That brings us to the end of this deep dive into LangGraph. We have covered everything from core concepts and state management through human-in-the-loop patterns to production deployment strategies. I hope this gives you a solid foundation for building your own production-grade AI agents. If you find this useful or you have any feedback for me, please feel free to let me know. Thank you and have a nice day. Bye.